Hi guys, in this part of our course we are going to examine a circuit which is quite common to class 10 exams, and the circuit looks like this, where you have resistances in parallel as well as series. So you might have various variations to this circuit, but the basic setup is what is being drawn on the board. You'll be given the values of the resistance, you'll be given the voltage of the battery, and you would be asked to find out the current in each of the branch. Apart from finding the current in the overall branch, you'll be asked to find the current in each of the branch. So finding the current in each of the branch will be quite interesting. And before we go on to do that, let me just recap the very basic. Like if two resistances were in series, what do you do about it? And if two resistances were in parallel, how do you solve that? So suppose a 1 ohm resistance was in series with a 2 ohm resistance and you have a 6 volt battery. Now how do you get what is the current in the circuit? So we know that the current in the first resistance will be the current in the next resistance because there is no other path. These two are in series, and the current coming out of the battery would be the current in these two resistances, which will come back to the battery. So we know all that, we have done all that. How to do this? The 6 volt is not appearing across 1 ohm, 6 volt is not appearing across 2 ohms. So the current over here cannot be 6 by 1, it cannot be 6 by 2 over here. 6 by 1 gives you 6 amps, 6 by 2 gives you 3 amps. So that is quite weird that a current of 6 amps goes through this and 3 amp goes through that. That's impossible. So what is happening is, through the basics, we have found out that a part voltage appears over here, part voltage appears over there, and the net voltage, that part plus that part, that drop, voltage drop from across the first ohm resistance plus the voltage drop across the second ohm resistance is the voltage drop across these 2 points, and the voltage drop across these 2 points is same as the voltage drop across the battery. So because this point is literally that point, so we had named that as equipotential points, and this point is literally that point. So the voltage across these two together is 6 volts. These two resistances, we had figured out that together it is a 3 ohm. It was a simple addition of 1 and 2, that is a 3 ohm resistance. So it's a 3 ohm resistance. So we'll redraw the circuit and make the equivalent circuit. So this circuit is equivalent to this, where you have the same battery, same 6 volt battery, and we have proved earlier that this 1 and 2 would together behave like a 3 ohm resistance. Now the 6 volt appears to that. Now in the V is equal to IR formula, we can put the voltage across the resistance. The V is voltage across the resistance. We can safely say that the voltage across the resistance is the voltage of the battery, because this point is literally this point and this point is that point, and hence the current in the resistance, that is the current in the resistance, would be given by 6 is equal to I times R, which is 3, and you get your I is equal to 2 amps. Since 2 amp is going in here, 2 amp must be going back to the battery and 2 amp must be coming out from the battery. So 2 amp is the current in the circuit. So we go back and we can say safely that the current coming out of the battery, this was equivalent. So current coming out of the battery is 2 amp, going in the battery is 2 amp. The current has no other path to go. 2 amp is going in this and 2 amp is going in that. We can have a bit of cross check over here with the help of this formula V is equal to IR, which is voltage drop across a certain resistance if the current in the resistance is known. So what is the voltage drop across this 1 ohm resistance? What do you think is the voltage drop? Yes, it is 2 into 1, which is 2 volts. Similarly, what is the voltage drop across this? What is the potential drop across this resistor? It is 2 into 2, which is 4 volts. So drop of 2 and a further drop of 4 means a total drop of 6, which is right. So the voltage change is equal to 6 across these 2 points. That cross verifies our solution of the circuit. In a slightly different way, I can say this point was having 0 potential. We assume it is 0 potential, say, then this would be 6 volts because the voltage across is 6. I could have assumed this as 10 volts and this will become 16, but I don't want to confuse you. Let this be 0, so this point is 6. The potential on these points are 666. Then this formula says that you drop in potential by 2. So the potential over here will become 4 volts. Potential at a point. It's not like potential across 2 points. Potential at this point will become 4 volts. And then you draw further 4 and the potential over here will become 0 volts. So the potential over here whole line was your 6 volts. So 6 to 4 it becomes, and then this whole line is 4 volts, and 4 to 0 it becomes. Had it been 10, what I was saying, this would have been 16 because the potential difference of the battery is 6 volts, mind you. So this would have been 16, and a drop of 2 would have given a 14 over here, and a further drop of 4 would have given a 10 over here. So this would have been 10, 10, 10, 10, 10 volts, which agrees with this 10 volt over there, had it been 10 volts. Anyways, so this is a very, very, very basic circuit of two things, two resistors being in series. So similarly, another basic circuit of two resistors being in parallel. Say I take a 2 ohm and a 3 ohm. In parallel with a battery of potential difference 6 volts across it. So again you can assume this is 0 volts over here and this is 6 volts over there. Now what would be the total current and what would be the current individually? Now what would be the current individually is the first thing what we can find over here without even going for the formula of resistances in parallel. So that formula was basically derived by using the fact that the potential across this branch is the potential across the whole stack. The potential difference across these 2 points is the potential difference across these 2 points, because there is no resistance in between from here to there. There is no resistance in between from here to there. So the potential drop cannot be anything from here to there according to that formula, V is equal to IR. So if you have no potential drop over here, this point is this point, that point is that point. And what was the potential across these 2 points? There is no drop over here because there is no resistance. So if I assume this potential was 0, then this is also 0. If I assume this was 6, then this point is also 6. So the voltage drop across the whole stack was 6 volts. So voltage drop across individual branches will also be 6 volts. So this becomes 6 volts. So you see, in a parallel circuit, 6 volt, which was the voltage of the battery, is a voltage which appears across the resistance which has been put in parallel in this kind of a setup, and this very 6 volt will be across this resistance also, because this point is literally this point and this point is literally that point. That is how the various equipments in your house are. Like this is a fan, there's a tube light, and that's your supply of RMS 220 volts. Then you get a 220 volt across each of the equipment, whether you have switched it on or switched it off. If I switch off this, I disconnect this, still the voltage across this is the same, 6 volts, and whatever current has to flow flows. So we have discussed all this before. I'll just emphasize on one point again, that why is this potential same as this potential? Because if I want to know the potential drop across any 2 points, I apply that formula, V is equal to IR, where V is the potential drop across the 2 points being studied, I is the current in that section of the resistor, and R is the resistance in that section of the conductor, in fact, and R is the resistance of that conductor. So over here, whatever is the current in this, I don't know, we are going to calculate. It is some current, it's not like it's zero current, but the resistance from here to there, the resistance is 0. So this part is 0. Hence IR gives you 0. IR becomes 0, that means the potential drop across this point to this point, the potential drop from this point to this point is 0. Hence, whatever is the potential over here is the potential over there. So what do we get? What do we get after getting the potential across these two resistors? The potential across this is 6, the resistance is 3, hence the current is 6 by 3, which is 2 amps. Similarly, the potential across this is 6 and the resistance is 2. So the current in this is 6 by 2, which is 3 amps. This is what you'll expect if the current is coming. If a certain current is coming, more will go towards the lesser resistive path and less will go towards the more resistive path. So the resistance was not that different. It was slightly less, hence the current is slightly more. And this is more, hence the current is less. So if this is the split of the current, then what would have been the total current? The total current would have been 5 amps. Absolutely right. It would have been 5 amps. And these two, 3, it splits into 3 and 2. They join back again as 3 and 2 and becomes 5 amps again. So whatever is coming out of the battery, which is 5 amp, comes back into the battery, which is 5 amps. Right? So this is the solution. And there was no need of the formula where we convert these two or represent these two resistances as a single resistance of what value? Of a value 6 by 5. Right? Had we done that, we would have got 1 by R equivalent of the parallel stuff is equal to 1 by 2 plus 1 by 3, which would have given us a 3 plus 2, which is 5 by 6. Hence R equivalent would have been 6 by 5 ohms. Had we done that, this circuit would have looked like this, very similar to this one. It would have looked like this. This is equivalent to that, we agree. The voltage across the resistance is 6 volts, because that's a single resistance. It becomes a setup like this, that's 6 volts, and we apply V is equal to IR for this, and we get 6 by 6 by 5, which gives us 5 amps in the resistance. But then we can argue that there is no other way to go, so the current is 5 amps all over. So the current is 5 amps all over, and we get this answer. We get this 5 amps. That's what we get. But do we get this 2 and 3? No, we don't. We have lost the division and we have represented as a single one. So doing this math, getting the resistance right, and then getting the current, the total current is first of all, it's longer than this. This was straight away a 6 by 3 and a 6 by 2. The explanation was long, but when you know what is happening, then you know the voltage across this is 6, and you simply do a 6 by 3 to get the current in this resistance, and similarly a 6 by 2 to get the current in that. And once you get the current, you know the total current. So you not only know the total current, which is 5 amps, but also the division, which is a 3 and 2. So this is a better way of solving than this way. So do not do this way unless it is required, and that unless it is required comes over here. I hope you know that why. Because had I given you 6 volts again, and what was this, 3 ohms and 2 ohms, would you say that the current in this is 6 by 3, which is 2 amps? Would you say that the current in this is 2 amps? Will you say that? Absolutely wrong. Why wrong? Because the voltage 6 volt doesn't appear across the resistance. Why it doesn't appear across the resistance? Because if I call this as 0 volts and this has 6 volt potential, the 0 volt potential is all over this line. We agree totally. All of this is 0 volt, 0 volt, 0 volt. But is this other end 6 volt, and hence is the potential difference 6 volts? Not at all, because 6 volts is here, 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 here till this point, and then the potential is going to drop by that formula V is equal to IR, because some current is going to flow in this, and it has got a certain resistance. So the resistance into the current multiplied with the current will give you the drop, and the voltage over here will become 6 minus whatever the drop is, and hence this point is going to have voltage less than 6. So all these points are going to have a voltage less than 6. So we don't know the voltage across this. So if you don't know the voltage across this, you can't simply do a 6 by 3, which is wrong, which is absolutely wrong. Got the point? So here the formula will come for a rescue, but not in these simple cases. When you directly know the voltage, when you know the voltage across a resistance, apply this. When you don't know the voltage across a resistance, try to find that. So that is what we are going to do. We'll try to find what is the voltage across this. So I hope you know the two basic setups. I hope you understand why this becomes a bit of a problem, because the voltage 6 volt is not appearing across this. Hence the current in this is not a 6 by whatever value I had given to it. Say I had given a value of 1 ohm to it. The current in this is not 6 by 1, which gives you 6 by 1 gives you 6 amperes, right? 6 by 3 gives you 2 amperes, which is a big cross by the way, and 6 by 2 gives you 3 amperes. This is all wrong. This is all wrong. First of all, a 6 ampere will come. A 6 ampere will come. When it divides, it can't become a 2 and 3. The total has to be 6. 2 and 3 is 5. So the math is also not going right. 2 ampere, 3 amperes joined becomes 5 amps. A battery is taking 5 amps, giving 6 amp is all wrong. It's all wrong. So this is not what is happening. This 6 by 1, 6 by 3, 6 by 2 is not happening. So V is equal to IR. In this formula, V is equal to IR. V is not the it is not the voltage of battery. I hope you understand. Not the voltage of battery. V is equal to IR. In V is equal to IR, V might be the voltage of the battery in few selective cases like this one when you have a single resistance, or this one when you had nothing over here, no resistance over there, and the voltage across the battery was the voltage across each of the resistance in the parallel stack. Otherwise, V is equal to IR might not be the voltage of the battery, and that might is like the bigger probability. So more often than not, it is not going to be the voltage of the battery. Anyways, the formula is not for the voltage across the battery. The formula is the voltage drop across a resistance carrying current I. So guys, let us solve this circuit, and then we'll do some variations on this basic setup. So what you have to find is what is the total current coming out of the battery, what is the current going in each branch of this parallel stack, what is the current in this 3 ohm resistance, what is the current through this 2 ohm resistance, and then obviously what is the current coming back into the battery, which is the current going out of the battery. And then in the process of solving, you'll comment on the voltage drop across each of these resistances. What is the voltage drop across this? What is the voltage drop across that? What is the voltage drop across that? So I want that V I for all the R's given. V and I, what is the current in this? What is the voltage across this? What is the current in this? What is the voltage across this? And what is the current in this and voltage across that? So I'll give you a minute for this. Do it fast and then resume the video. I hope all of you have got the solution. Verify your solution along with me. So, and I hope that none of you have written that the current in this is 11 by 3, current in that is 11 by 2, current in this is 11 by 1, because nothing is going to fit in if that is what you write, and that is absolutely wrong. So I hope you have got that. So the point is, this circuit cannot be solved unless until we draw an equivalent circuit of it, we resolve the resistances. So we'll do that step by step. These two are in parallel for sure. So what we'll do is, why they are in parallel? Because the current has split at this point and those two currents are going to join. So this branch is in parallel with that branch for sure, and the value of these two as a single equivalent resistance would be 2 into 3 by 2 plus 3, which is 5. So it will be a 6 by 5. So I'm going to write that directly. So the circuit will look like this now. 1 ohm is where it was, and these two have become 6 by 5 ohms. That has become a 6 by 5 ohms, and the rest of the circuit was as it was. 11 volts is what is given. So this circuit is equivalent setup of this. This and this is the same circuit, right? Now how to do this? Is 11 volt appearing across this? Is 11 volt appearing across that? No, it is not. So we have to further solve it as it was shown earlier. So on further solving it, what we'll get is a single resistance of these two. So that is 1 plus a 6 by 5. That's a 5 by 5 plus 6 by 5, which is 11 by 5 and 11 by 5 ohms, and the same battery of 11 volts. Now we can apply the formula safely. V is equal to IR, because now we know the voltage across this. We did not know the voltage across this here. It was not 11. We did not know the voltage across this guy. It was not 11. We did not know the voltage across this one or that one. So we were resolving, and we come to a point where we know the voltage across this. So what is the voltage across that? The voltage across this is full 11 volts. Easy numbers for us. So V we put as 11, R we put as 11 by 5, 11 by 5, and we'll get our current I equal to 5 amps. So what we see is there is 5 amp flowing in this, 5 amps flowing in this. That means the battery was supplying 5 amps, and 5 amp was flowing in the circuit. In this equivalent circuit, 5 amp is flowing. This circuit is equivalent to this, which translates to the battery over here is supplying 5 amps, because the battery was supplying 5 amps. So 5 amp goes out, 5 amps comes in. So 5 amp is going through this, 5 amp is going through this. So that is what we are going to label. So that was what we were trying to find. We were trying to find the V, I and R for each resistance. So we have got the current in this resistance. We yet do not know the current in these two individually. We know that together 5 amp has gone, which is obvious. If 5 amp is flowing through this, then overall 5 amp has gone into this, but how much into this and how much into that is yet to be calculated. Now two ways you can calculate that, but let me just come back to this circuit and emphasize that what we have got is the current flowing through this resistance and the current flowing through the equivalent of these two resistances. So that current goes back into the battery. So once we have labeled everything, we'll come to this. One more labeling is remaining over there, and that labeling would be the voltage across this one and across this one. So what do you think is the voltage across this? If we keep doing our work properly, if we keep finding out each and everything what is required for resistance, which is V and I for the resistance, I we have found, V also, it is going to help us subsequently. So what is the voltage across this? Voltage across a certain resistance is current in that resistance into resistance value of that resistor. So 1 into 5, which gives us 5 volts. Now what is the voltage across this one, the other guy? Again you can do a V is equal to IR, or you can say that the total voltage was 11. Total voltage across these 2 points is 11. The potential drop is 11, out of which this is a drop of 5. So this has to be a drop of 6, so that the total drop becomes 11. 5 plus 6 is 11. So 11 minus 5 you can do, or you can do I into R. So I'll do a I into R over here. I was 5 and R is 6 by 5. So 6 by 5 into 5 gives us 6 volts. So are we not verifying that 5 volt plus 6 volt is 11 volts? So if this kind of verification is happening, there is no chance that you are going wrong in the circuit. There is no chance you are going wrong in the circuit. Now whatever we have found out over here, we are going to label it over here. A 5 amp was flowing through 1 ohm. We had written that. What's the voltage across this? The voltage across this is 5 volts. Now what is this 6 by 5 ohm? 6 by 5 ohm was from here to there. It was from this point to this point. So 5 totally was going in this, so we can't label. It has got some division. But the voltage across those 2 points, this point is this point, that point is that point. So voltage across those 2 points was 6 volts. So this voltage must be 6 volts. Again, you can check out that the total voltage from here to there is 11 volts, out of which 5 was a drop here. So this must be a drop of 6. 5 plus 6 is 11. Now once you have got the voltage across a parallel stack, that is what we had in one of the simpler circuits earlier in the video. So if you have the voltage across the parallel stack, that voltage is going to appear across each of the resistance, because this point will be this point will be that point. Hence the voltage across this one, voltage across the 3 ohm guy is 6. Voltage across that one is also 6 volts. So once we know out of the 3 things V, I, R, once we know 2 of the things, R is known, we got the V, we'll quickly put the formula V is equal to IR and get the third thing. So 6 by 2 is going to give me 3 amps, and a 6 by 3 is going to give me 2 amps. And a cross verification would be 3 plus 2 gives a 5 amp. So 3 plus 2 is 5. So that addition would not have happened if all our math would not have been correct. So 3 plus 2 is 5 amp, which comes back to the battery, which was flowing out of the battery. So that's the solution to this circuit. I'll just quickly go through the solution again. I'll just quickly recap. Since you did not know the voltage across each of them, like this 6, we did not know. We had this 11 value. We had to find out that 6 value. So what we did is, we did what we can. That is, make the 2 resistance in parallel as a single resistance. We got that single resistance. Then the 2 resistances were in series. We got the net resistance, and hence the net current coming out of the battery. So we figured out what is the current going in each of these 2 resistances. Once we got that current, we got the voltage across each of the resistances. So once you get the current, by the way, you can straight away jump to this circuit. Once you get the current, once you get the current, when you jump to this circuit, you know the current in this is 5 amp. The current coming out of the battery is 5 amp. So the current going in this is 5 amp. So you know the voltage across this. The voltage across this would be 5 volt. 5 into 1 is 5 volt. Net voltage was 11. So 11 minus 5 will give you 6 volts. So you know the voltage across this. This was the main thing to find out. Once we have found out the voltage across this, we know the voltage across individual resistors would be same. So 6 by 2 and 6 by 3 gives us the individual currents, and that's our answer. I'll give you another circuit of a similar kind. One more thing, what you can see over here is the current is in opposite ratio to the resistance, which is nothing surprising, because if 2 resistances are in parallel, R1, R2, and say the current in them is I1 and I2, then we say I1 by I2 is equal to R2 by R1. It is the opposite ratio of the resistance, and we do the ratio thing only when 2 resistances are there. If there is 3 resistance, 4 resistance, we'll do the basic. And what is the basic? What is the basic format of this? The basic format is the voltage drop is I1 R1, and the voltage drop across that is equal to I2 R2, voltage drop across this is going to be the voltage drop across that. So I1 R1 is going to be equal to I2 R2, and hence when you cross multiply, you'll get a I1 by I2 is equal to R2 by R1. This is the right thing to do, and remember this, I would say don't go by this. Don't go by this. Why? Because if you have three resistances, there was a R3 over here. Then again this is going to hold R1 is equal to I2 R2 will be equal to I3 R3. But you might mess up the stuff if you are using ratios. So guys, I hope that you have understood the solution of the previous circuit very well. So this circuit is having basically the same essence. So it is virtually you have to do the same steps to solve it. So what you have to get is you have to get the voltage and the current in each resistance, voltage across each resistance and current in each resistance. This one, 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 all individually. I want to know the V. I want to know the I in each of the R's given to you. And I also hope that you have understood that V is equal to IR formula was not for the voltage of the battery. It was the voltage across a certain resistance in which I current is going. So nobody is going to do a 28 by 1 to get the current in this as a 28. That's absolutely wrong. Or a 28 by 2 to get the current in that. So if you are on YouTube, pause the video now and resume after you have solved to see the solution along with me. And suppose you are on our software, then it will pause for itself. Yeah, the solution now. So what do you do? To get the current in individual resistance, we need to know the voltage. Among these two, we should be knowing one to get the other. Either this to know that or that to know this. R is given to us. So what we can do, will do, that is simplify it and make equivalent circuits. So equivalent circuit would be a 2 ohm and 2 ohm in parallel will give you 1 ohm. I guess you have got that. This 1 ohm is the original 1 ohm which was already there. So that's 1 ohm. And a 1 and a 2 and a 3 in parallel. I hope you have made 1 plus 1 as 2R, 2 ohms. So 1 ohm, 2 ohm and 3 ohm in parallel is going to give me a equivalent resistance given by 1 by R is equal to 1 by 1 plus 1 by 2 plus 1 by 3. So you can take the LCM as 6, and what you'll get is 11 by 6 is your 1 by R. So do not forget that your R is reciprocal of that. So do not do that mistake in your hurry and scurry and spoil your case. So your R, equivalent R for that parallel stack becomes 6 by 11 ohms. That's your reduced circuit. That 28 volts remain as 28 volts. So further, if you want to draw, you may draw or you may omit drawing. I'll just draw it for you. That again we know that this 28 volt is not appearing across this or this or this, but it is appearing across the net resistance of these three. These three are in series now. So the net resistance will be a simple addition of 6 by 11 with a 1 and a 1. So what you get is 6 by 11 plus 11 by 11 plus 11 by 11. So that 11 plus 11 is 22 plus 6 is 28. So what you get is 28 by 11 ohms. Nice number. 28 is the voltage of the battery. So we hope that some easy cancellations and calculations will happen. So that's your reduced circuit. So this circuit is equivalent to this. So current here I can find out, but that current cannot tell me how much current is going into this or this or this. But what this will reveal will help us get something over here, and what this will reveal will get us the ultimate solution what we want. So the current in this circuit would be 28 volts divided by 28 by 11, which gives us 11 amps. So 11 amp is going out of the battery and coming back into the battery. That is what is happening. 11 amps is coming out of the battery and going back into the battery because 11 amp is flowing in this resistance. This is not one resistance, this is a combination of resistances. So what we get from this circuit is 11 amps is going out and 11 amps is coming in. Easily we can see that there is no path and all of them are having 11 amps, 11 amps, 11 amps. That is our aim. Among the VIR, get two things so that you get the third thing. I got two things. I got the R, I got the I. I'll get the third thing. What is the third thing? The third thing is V. I'll get the voltage across this. Do I require it? I'll just get it anyhow, whether I feel I require it or not, because I'm solving the circuit, and this solution of this intermediate circuit is going to carry back to that main circuit. So voltage across this resistance would be current in the resistance into resistance value of that resistance, which is 11 into 1, that is 11 volts. How much is that? 11 into 1 again, which is 11 volts. How much is that? 6 by 11 into 11, which is 6 volts. Do they add up to 28? 11 plus 11 plus 6 is 28. So clearly our calculations till now is right. Otherwise this kind of cross match is not going to happen. So we have matched our potential drop with the individual drops. Individual drops added is the net potential drop across this, which is matching with the voltage of the battery. So we are quite confident that our calculations are going right. Now we'll copy paste what we have got over here into our main circuit, because this was our main circuit. So where is this 11 volt? Where is this 11 amp? 11 amp is here in both of them somehow. So 11 volt is across the 2 points, across the resistance. So that resistance was here to here. So that is your 11 volts. From here to here, that's your 11 volts. And then what is this 11 volt across these 2 points? That's 11 volt again. And what is that 6 volt? That 6 volt is across these 2 points. So that's your 6 volts. So whatever results we had got over here, we have put it over there. 11 amp was the current flowing in here. I'll write 11 amps. 11 amp was totally going in this. Both the resistance is are same, so we don't have a preference any one place. So most probably that the current which is getting divided is equal. It has to be equal in both of it, but we'll just go by V is equal to IR all the time, so that we have a habit of using that. So voltage across this 2 ohm is the voltage across the parallel stack, which is 11. Hence the current in this is 11 by 2, which is 5.5 amps. And here again voltage across 2 is voltage across the whole stack, which is 11 volts. So the current in this, using the formula V is equal to IR, is equal to 11 by 2, which is 5.5 ohms. And that had to be because the resistances are equal, so the current prefers both the path equally. So in that sense, which path is least preferred in this? This one is the least preferred path, and this is the most preferred path. So when we are going to get the currents, I hope the current in this is going to come more than the current in that. So this 5.5 11 amps was coming. This 11 amp, I'm straight away writing from here that 11 amp was coming. That 11 amp is coming. That 11 amp is getting divided into 5.5. Joins back again, becomes 11 amp, gives a potential drop of 11 further. The potential over here was 28, it dropped by 11 and has become 28 minus 11, which is 17, drops further by 11, becomes 17 minus 11, which is 6, and then drops by a 6 and becomes 0. Okay. So the current in these three branches, what is the current in the top branch? 6 by 1, because the voltage across that would be 6 by 1, which is 6 amps. I hope the addition comes as 11 amp. 6 by 3 is the current in the bottommost branch, which is 6 by 3 is 2 amps. 2 amp is the current in the bottommost branch. And what is the resistance of this branch? These two 1 ohm is in fact a 2 ohm resistance. So your 6 volt is not across 1. The 6 volt is not across 1. You will not do a 6 by 1 and a 6 by 1 and get 6 amps and 6 amp, which is 12 amp, which is absolutely wrong, which doesn't mean anything. I mean 6 ampere 6 ampere doesn't mean 12 amp, by the way, and it doesn't mean anything. So what is the voltage across this thing? Voltage across this thing is 6 volts. The total resistance is 2 ohms. So 6 by 2, 6 by 2 gives me 3 amps. Does it add up to 11? 6 plus 3 is 9, 9 plus 2 is 11. So we are absolutely right. This cross matching would not have happened had our calculations not been right. So that's our final answer. Individual currents and individual voltages for each resistance. For this 2 ohm it is 11 volts and 5.5 amps. Same for this. For this it is 11 volts and 11 amps. For this guy it is 6 volts and 6 amps. For this guy it is 6 volts and 2 amps. And individual for this we have not found out yet. I'll just write that also. So the individual voltage across this would be, this was 6 volts, both are same resistances, so I guess that will have same drop. It will have a 3 drop here and a 3 drop there, but then we'll make our intuition doubly sure using the formula. The current in this is 3 amps, the resistance is 1, so when we apply a 3 into 1, 3 into 1 we get 3 volts. So this is your 3 volts. Same current is going into this. That 3 current in a resistance of 1 ohm gives you a voltage drop of 3 into 1 again, which is 3 volts. Sorry, 3 volts over here. So what we are getting is 3 volts plus 3 volt is a 6 volt drop across the whole thing. So now we have got the currents in each resistance what was asked and the voltage across each resistance. That was the question and we are done with it. So this is the variation what you can have is like more resistances, more stuff in series, more stuff in parallel, some extra stuff over here. If I add something over here, that thing, is it in parallel with this are the three things in parallel? No, obviously not. This one is in series with this and that. The current going through this goes through that, then goes through this. So you can add up resistances, but the essence of solving remains same. You have to reduce it to a single resistance and a single battery, get the current, then get the current in each resistances, get the voltage across it. Once you got the voltage across, you map it back to the original question and do the rest. So that's it guys. So quiz will follow after this video and I hope you get your quiz questions right. Bye bye.